Dear student, welcome to CET and NEET preparations for the chapter 4 of the second PUC, Moving Charges and Magnetism. So here we are in this class we are going to discuss about some NEET and CET questions which are appeared in this chapter, Moving Charges and Magnetism. Okay. Now, before going to solve some problems, we will list out some important formulae which are coming in this chapter. Now, first formula we have the force experienced by a moving charge in the presence of an external magnetic field. So that is given by F is equal to QVB sin theta. Q is the charge, V is the velocity of the charged particle, and B is the magnetic field. It is a vector quantity. It can also be written as Q into V cross B. V is the velocity vector and B is the field vector. And the second important formula is magnetic force experienced by a current carrying conductor. If you have a conductor which carries a current of I and it's having a length of L, then the magnetic force experienced by the current carrying conductor is given by F is equal to I into L into B sin theta. So theta is the angle between L, the length of the current element, and B, the magnetic field. And next formula is whenever a charged particle is moving perpendicular to the magnetic field, it is moving perpendicular to the direction of the magnetic field, then it describes a circular path, and the radius of that circular path is given by R is equal to m into V divided by Q into B. Now m into V is nothing but the momentum. Therefore, if they ask in some problems in terms of momentum, then we can write it as P divided by Q into B. Now we know the relation between the kinetic energy and the momentum. So P is equal to square root of 2mk divided by Q into B. Now this is a very important relation. In some problems they may ask if the kinetic energy of the particles are equal, then what is the relation between the radius? They will ask like that. In that case, from this formula, if k is constant, that is kinetic energy of all the particles are constant, then what about the radius? Now radius is directly proportional to square root of the mass and inversely proportional to the charge. Look at that formula. Therefore, you should remember this very important formula, R proportional to root m by q. And angular frequency is given by omega is equal to V divided by R. From the above formula, we can write it as QB divided by M. Similarly, the linear frequency is given by nu is equal to QB divided by 2 pi M. And if they ask for the time period, we have to take the reciprocal. Therefore, time period T is equal to 2 pi M divided by Q into B. Now, further moving, the next one, if the charged particle is moving in a helical motion, when it moves in helical motion, if the velocity component of the charged particle has a component along the field direction, that is magnetic field direction, then it describes an helical path, and the distance moved in one time period is called the pitch and is given by the formula V parallel into T. We know the value of T, it is 2 pi M divided by QB into V parallel. V parallel can also be written as V cos theta. It is the horizontal component of velocity. And next one is velocity selector. When a charged particle is moving in both electric field vector and the magnetic field vector, which are mutually perpendicular to each other, then the velocity of the charged particle is decided by the magnitude of these two fields, that is velocity V is equal to electric field vector E divided by magnetic field vector B, their magnitude. Okay. So then cyclotron, it is a device which is going to accelerate the charged particles, and the frequency of the cyclotron is known by nu c is equal to qb divided by 2 pi m. Now this is very important one. Now this cyclotron frequency is independent of kinetic energy of the charged particle which is revolving. That is very important one. Now kinetic energy of the ion or the charged particle which is coming out of the cyclotron is given by K is equal to Q square B square R square divided by 2m. K is equal to B square Q square R square divided by 2m. And from this relation, so if they ask for to find the potential, then this should be is equal to Q into V, we should remember. Next one is Biot-Savart's law and is given by the magnetic field due to a current element dB at some point is given by mu naught divided by 4 pi into IDL sin theta divided by R square. Now this is obtained for an infinite length conductor. If a conductor having a finite length, then the formula is modified, that is mu naught divided by 4 pi into I by R into sin theta 1 plus sin theta 2. Theta 1 and theta 2 are the angles subtended by the ends of the conductor at the given point. So next one is Ampere circuit law. Now this is a very important one, that is line integral of B dot dl is equal to mu naught times the current enclosed by that loop, that is Amperian loop ಅಂತ ಕರೀತೇವೆ. So therefore B, it is the magnetic field at the given point that we are going to calculate, and L is length of the Amperian loop, that is the boundary of the Amperian loop. And here mu naught into I is the current enclosed by the Amperian loop. That should be a very important concept one. Next, the force between two parallel conductors. That means if you have a two conductors, along the two conductors, if the current is flowing in the same direction, then the force between the parallel conductors is given by F is equal to mu naught into IA into IB into L divided by 2 pi D. This is one formula where D is the distance of separation between the two conductors. Now the torque experienced by a current loop placed in an uniform magnetic field is given by tau is equal to N into I into A into B sin theta. N is the total number of turns in the coil, and I, the current flowing through the coil, A, area of cross section, and B, the magnetic field into sin theta. Therefore tau is equal to M, it can also be written as M cross B. The magnetic moment is given by M is equal to N into I into A. Okay. Next formula, the magnetic moment of revolving electron mu L is given by minus E into vector L, where L is the orbital angular momentum, divided by 2 into ME. ME is the mass of the electron. Now we know that a galvanometer can be converted into ammeter as well as voltmeter. It can be converted into ammeter by connecting a low resistance in parallel, and that low resistance is called the shunt resistance and is given by Rs is equal to Ig into Rg. Rg is the resistance of the galvanometer divided by I minus Ig. Similarly, galvanometer can be converted into voltmeter by connecting a high resistance in series. The value of the high resistance is given by this formula, R is equal to V by Ig minus Rg, where Ig is the full scale deflection current. Now with these formulas, now we are going to solve some problems. First problem, the correct Biot-Savart's law in vector form is options A, vector dB is equal to mu naught divided by 4 pi into I into dl cross R divided by R square, and B, dB is equal to mu naught divided by 4 pi into I into dl cross R divided by R cube, and C, dB is equal to mu naught divided by 4 pi into I dl divided by R square, and D, dB is equal to mu naught divided by 4 pi into I dl divided by R cube. It is simply a theoretical one. The vector form of Biot-Savart's law, we know that vector dB is equal to mu naught divided by 4 pi into I into dl cross R. dl cross R. Since it is a cross product, dl cross R is in the numerator, Therefore, denominator should be r cube. Hence, B is the right answer. Okay. Second problem. An electron is moving in a circle of radius r in a uniform magnetic field B. Suddenly, the back field is reduced by B by 2. Then the radius of the circular path now becomes, an electron is initially revolving, therefore the magnetic field is B. As and when the field is reduced, what about the radius of the electron? The options are now A r by 2, B 2r, C r by 4 and D 4r. Now we know that radius is given by the formula r is equal to mv by q into b. That means radius is inversely proportional to the field. Now look at that formula, r is equal to mv divided by qb. Therefore radius is inversely proportional to the magnetic field. As the field is reduced to half, then obviously radius has to be increased by 2. Therefore B is the right answer, that is radius becomes 2r. Next problem. A charge q is accelerated through a potential difference capital V. It is then passed normally through a uniform magnetic field where it moves in a circle of radius r. The potential difference required to move it in a circle of radius 2r. Now we have a charge q. Now it is accelerated through a potential v. Then it is passed through a magnetic field. When a charged particle passes normally through a magnetic field, it describes a circular path we know. And they have given radius is r. Now I have to increase the radius. In order to increase the radius to 2r, what should be the potential? That we have to calculate. Now options are now A 2 volts, B 4 volts, C 1 volt and D 3 volts. We know that kinetic energy of a revolving electron or revolving charged particle in cyclotron case we have studied, K is equal to B square Q square R square divided by 2m. Now according to first year concept, the change in kinetic energy is equal to the work done. Now work done is, here in this case work done in order to move a charge in a potential V is Q into capital V. Now look at that one. Kinetic energy K is equal to Q square B square R square divided by 2m, and that should be is equal to work done, that is Q into capital V. Now here capital V is the potential. Now from this simple relation, now what is the potential? Now potential is directly proportional to the square of the radius of the orbit. Therefore V proportional to r square. Now in the first case, the voltage is V1 and the radius is r. Therefore V1 proportional to r square, first case. Now in the second case, we have to increase the radius r2. In order to r is equal to 2r. In order to raise the radius, what should be the potential? Let me take it as V2. V2 is the potential required to increase the radius to 2r. Therefore, V2 should proportional to 2r whole square. 2r whole square becomes 4r square. Now take the ratio of those two. That is V2 divided by V1 is equal to 4r square divided by r square. Now r square get cancels. Therefore, the new potential required to increase the radius to 2r is V2 is equal to 4V, and hence the option B is the right answer, 4V. Okay. Now here one thing we should remember, potential is directly proportional to the square of the radius. Next problem. A cyclotron is used to accelerate. Purely theoretical one. Look at the options. 1. A. Only negatively charged particles. B. Neutrons. C. Both positively and negatively charged particles. D. Only positively charged particles. We know that according to theory, a cyclotron is a machine used to accelerate any charged particle, either it is positive or it is negative. So based on that one, C is the right answer, both positively and negatively charged particles. So it's going to accelerate these two particles. C is the right answer here. Next problem. The magnetic field at the center of a current carrying loop. They have given the magnetic field at the center of the current carrying loop is 5 root 5 times the magnetic field at a point along its axis, and they have given the radius of the coil as 0.1 meter. The distance of this point from the center of the loop is, now we have to calculate axial distance point. Okay, options: A 0.25 meter, B 0.2 meter, C 0.05 meter, and D 0.1 meter. Now here we have a circular loop. In the case of a circular loop, they have given magnetic field at the center, which is 5 root 5 times the magnetic field along the axial point. Now that is given. If I take B naught as the magnetic field at the center and B is the magnetic field along the axial point, then by data they have given B naught is equal to 5 root 5 into B. Now by using Biot-Savart law and writing the expression for magnetic field due to a circular loop at the center as well as along the axial point. Now what is the expression for B naught at the center? We have studied it is mu naught I divided by 2R. Mu naught I divided by 2R. So that is mu naught I divided by 2R, that is equal to 5 root 5 into, what is the expression for the magnetic field along the axial point? It is mu naught I R square divided by 2 into R square plus X square to the power of 3 by 2. Now from this step onwards, it is a simple mathematics. Now first cancel the terms, that is mu naught I by 2, which are common in both the sides, they get cancelled. Therefore I will get cancelling and cross multiplying. R square plus X square to the power of 3 by 2 is equal to 5 root 5 into R cube. Now squaring on both sides. If I square it, I will get R square plus X square to the power of whole cube is equal to 5 root 5 square. 5 square is 25, root 5 square is 5. Therefore 25 into 5 is 125. R cube is R to the power of 6. Okay. Now taking cube root on both sides. Next step is very important, that is taking cube root on both sides. Therefore we get R square plus X square is equal to 5 into R square. Now taking R square on one side and X square on another side, therefore I will get X square is equal to 4R square. Therefore what is the value of X? Taking the square root on both sides, I will get X is equal to 2R. But R is the radius of the circular loop, which is given 0.1. Therefore 2 into 0.1, it is 0.2 meter. Hence the distance of the point from the center is, along the axial point is, X is equal to 0.2 meter. Therefore B is the right answer here. Next problem. A straight wire of length 50 cm carries a current of 2.5 amps, is suspended mid-air by a uniform magnetic field of 0.5 Tesla. It is as shown in the figure. The mass of the wire is, now here we have to calculate what is the mass of the wire. Given acceleration due to gravity is G is equal to 10 meter per second square. Now look at the diagram. Now this is the diagram. Here we have a wire which is suspended mid-air. What are the options for the mass? A 250 gram, B 62.5 gram, C 100 gram, and D 125 grams. So here a wire which is carrying a current. Now it is suspended in mid-air. Why it is suspended? Now it is experiencing two forces. One is the gravitational force, that is weight, which is acting downwards, m into g. Now this is balanced by the magnetic force experienced by that current carrying wire. Now what is the direction of the magnetic force? Now direction is given by the familiar Fleming's left hand rule. We know that if you stretch the first three fingers of the left hand, the forefinger indicating the direction of the magnetic field, middle finger indicating the direction of flow of the current, then obviously the extended thumb indicates the direction of the magnetic force. Now with this help, now current is flowing from left to right side and the magnetic field is into the plane of pole and the extended thumb is upwards, and hence this current carrying wire, it experiences an upward magnetic force and obviously there is a downward gravitational force. Now these two are balanced. When these two are balanced, we have m into g is equal to ILB sin theta. Now here theta is 90 degree. Therefore m into g is equal to ILB. Therefore we are in need of mass. So m is equal to ILB divided by g. Now simply substitute the values. I is 2.5 and length is 50 centimeter. Now they have given in centimeter, we have to convert it into meter, therefore it is 0.5 into, and the magnetic field is 0.5 divided by G. G is, they have given 10. Now 0.5 into 0.5, it is 0.25. So 25 into 25, it is 625. If you use that concept, so 2.5 can be written as 25 into 10 to the power of minus 1. 0.5 into 0.5 is 0.25. It can also be written as 25 into 10 raised to minus 2. So in the numerator, 25 into 10 raised to minus 1 into 25 into 10 raised to minus 2. If you multiply 625 into 10 raised to minus 3. In the denominator, we have 10. If I take to the numerator, it becomes 625 into 10 raised to minus 4. If I remove 10 raised to minus 4, then it becomes 0.0625 kg. 0.0625 kg. If I write it in terms of grams, it is 62.5 grams. The value is 62.5 in grams if I divide it by 1000. So therefore B is the right answer, 62.5 grams. Next problem. A galvanometer of resistance 50 ohm is connected to a battery of 3 volt along a resistance of 2950 ohm in series. Show full scale deflection of 30 divisions. The additional series resistance required to reduce the deflection to 20 divisions. So here a galvanometer is connected to a series high resistance. That means we are going to convert a galvanometer into voltmeter. In the first case, it is going to have a full scale deflection for the 30 divisions. In the second case, we have to reduce the deflection to 20 divisions. In order to reduce the deflection, I have to increase the resistance of the galvanometer. The options are now 1500, B 7400, C 4450 and D 2950 ohms. Now in the first case, galvanometer is having a full scale deflection for 30 divisions. Okay, we know that the resistance to be connected R is equal to V by Ig minus Rg. V is the voltage, that is 3 volts. Ig, that is the full scale deflection current. Okay, that we have to calculate here in this formula. And R is given series resistance, that is high resistance 2950, and Rg, the resistance of the galvanometer is given, it is 50 ohm. Now we know the formula. Therefore from the resistance formula, R is equal to V by Ig minus Ig, V by Ig minus Rg. We can write the current Ig is equal to V divided by R plus Rg. Now V is 3 ohms and R is 2950 plus Rg, resistance of the galvanometer is 50, that is 3 by 3000, that is equal to 1 into 10 to minus 3 amps or 1 milliamps. So that is full scale deflection current whenever the galvanometer is having 30 divisions. Now in the second case, the galvanometer is having a 20 divisions. Current has to be decreased. In order to decrease the current, the series resistance has to be increased. How much we are going to increase the series resistance? Now, if I take that as RA, additional high resistance. Now the formula becomes the high resistance R is equal to V by Ig minus Rg. Now here capital R is the combination of the previous resistance 2950 and the additional resistance Ra. Therefore 2950 plus Ra. This is the additional resistance Ra. It should be equal to voltage is 3. Now here Ig becomes changed because in the previous case we have calculated Ig for 30 divisions, it is 1 milliamps, that is 1 into 10 to minus 3. Now what is the deflection for 20 divisions? That can be calculated 20 divided by 30 into the current for unit deflection 1 into 10 to minus 3 and minus of 50. Now simply the 30 in the denominator of the denominator goes to the numerator, it becomes 90 by 20 or 9 by 2. 9 by 2 becomes 4.5. Now in the denominator we have 10 raised to minus 3. If I take it to the numerator, we get 4.5 into 10 raised to plus 3. Now 10 raised to plus 3 is 1000. Therefore 4.5 into 10 raised to plus 3 is 4500 minus 50. Therefore we will get the answer 4450 ohms. But actually this is not the answer. Now this is both the initial resistance, series high resistance plus the additional resistance Ra. But here they have asked what is the additional resistance Ra. That we have to calculate. Therefore, Ra is equal to 4450 minus 2950. Now, if you subtract, I will get 1500 ohm. Hence, A is the right answer here. Next problem. A proton, a deuteron and an alpha particle are projected perpendicular to the direction of a uniform magnetic field with same kinetic energy. Here kinetic energy is same. The ratio of the radii of the circular paths described by them is, now look at the options. A 1 is to root 2 is to 1, B root 2 is to 1 is to 1, C 1 is to root 2 is to root 2 and D root 2 is to root 2 is to 1. Now we know that the expression for kinetic energy in the case of a particle moving in the magnetic field is given by K is equal to Q square B square R square divided by 2m. Since kinetic energy of all the particles are constant, that is same, therefore radius, we know that already, radius is directly proportional to square of the mass and inversely proportional to the charge. Therefore R proportional to root m by q. Now use this formula for all the three particles. First one is proton, that is Rp, is to second one is deuteron, Rd, is to third one is alpha particle, R alpha. Therefore Rp is to Rd is to R alpha is equal to mass of the proton, square root of mass of the proton divided by its charge is to square root of mass of the deuteron divided by its charge is to square root of mass of the alpha particle divided by its charge Q. If I take the masses of the proton as 1 unit, in the first case mass of the proton it is 1 unit, I will take it as root 1, and mass of the deuteron, it is having one proton and neutron, therefore its mass becomes 2, therefore second term is root 2. And mass of the alpha particle, it is having 2 protons and 2 neutrons, therefore mass of the alpha particle I will take it as 4 unit. Therefore I will substitute mp 1, md 2 and ma alpha particle, it is 4 masses. Now charge, proton charge it is 1, deuteron charge is also 1, alpha particle charge since it is having 2 protons it is 2. If I substitute these values, I will get root 1 divided by 1 is to root 2 divided by 1 is to root 4 divided by 2. Now third term, root 4 is 2, therefore 2 get cancelled, I am getting 1. Hence, the ratio of radius R proton is to Rd is to Ra should be equal to 1 is to root 2 is to 1. Now this is a very important formula. You should remember this important problem. You should remember this one. Frequently asked question, and hence option A is the right answer. So one thing you should remember here, if the kinetic energy of the particles are same, which are moving in a magnetic field, uniform magnetic field, then the radius r described by the particles is directly proportional to square root of their masses and inversely proportional to the charge. Very important formula. The next problem. A proton beam enters a magnetic field of 10 to minus 4 Weber per meter square. Normally, if the specific charge of the proton is 10 to 11, this is very important. Specific charge 10 to 11 coulomb per kg, and its velocity is 10 to 9 meter per second. Then the radius of the radius of the circle described will be, look at the options, A 100 meter, B 0.1 meter, C 1 meter, D 10 meter. Now, a charged particle moving normally in the presence of magnetic field describes a circular path, and its radius is given by R is equal to mv by q into b. Now here v is given, velocity is given, magnetic field is given, and charge to the mass ratio. Charge to the mass ratio, that is specific charge. What is the meaning of specific charge? It is the charge to the mass ratio, that is q by m is given, that is 10 to the power of 11. Therefore, I will rewrite the formula 1 divided by q by m into v divided by capital B. Now simply substitute the values. Now 1 divided by 10 to the power of 11. Now velocity 10 to the power of 9 divided by magnetic field 10 to minus 4. Now 10 to minus 4 goes to the numerator, therefore 9 plus 4 it is 10 to the power of 13. In the denominator it is 10 to the power of 11. If I take it to the numerator it becomes minus 11. 10 to the power of 13 minus 11 it is 10 to the power of 2. 10 to the power of 2 is 100 meter. Therefore radius is 100 meter and A is the right answer here. Next problem. A circular coil of radius 10 cm and 100 turns carries a current 1 amp. What is the magnetic moment of the coil? Now options: A 3 into 1.42 into 10 to the power of 4 ampere meter square, B 10 to the power of 4 ampere meter square, C 3.142 ampere meter square, and D 3 ampere meter square. Now here they have given a circular coil of radius 10 centimeter. Given in centimeter, we have to convert it to meter, and it is having 100 turns. Carries a current of 1 amp. Now magnetic moment is given by M is equal to N into I into A. What is capital N? The number of turns. I, current flowing through the coil, and A, it is the area of cross section. Since the coil is circular in nature, its A is given by pi into r square, radius. That no, M is equal to N into N-I-A. Now substitute for A, that is pi into r square. Now N is, it is 100 turns into I, current is 1 ampere into pi 3.142, and radius is 10 centimeter. If I substitute in terms of meter, it is 0.1 whole square. Now 0.1 square becomes 0.01, or it can be written as 10 to the power of minus 2, and here it is 100. 100 into 0.01, it becomes 1. Therefore, answer is 3.142 ampere meter square. Hence, C is the right answer here. Next problem. A galvanometer coil has a resistance of 50 ohm and the meter shows full scale deflection for a current of 5 milliamps. This galvanometer is converted into voltmeter of range 0 to 20 volts by connecting. Now here options are A 3950 ohms in parallel with the galvanometer, B 3950 ohms in series with the galvanometer, C 4050 ohms in parallel with the galvanometer, and D 4050 ohms in series with the galvanometer. Now carefully look at the problem. A galvanometer has to be converted into a voltmeter. How can you convert? By connecting a high resistance in series. With this knowledge and with the help of an elimination method, we can easily remove A and C. We can easily decide that A is not the right answer and C is not the right answer. Why? They have to be connected in parallel, resistance parallel they have given, but here we have to connect in series. So only B and D are the right answers. Now for the what should be the high resistance that we are going to calculate. High resistance R is given by V by Ig minus Rg, that is the formula. V, that is the voltage given 20 volts. Ig, full scale deflection current, it is 5 milliamps and given, and resistance of the galvanometer is 50. Now substituting the values, it is 20 divided by 5 into 10 to the power of minus 3 minus 50. 20 by 5, it is 4. 10 to the power of minus 3 goes to the numerator. 4 into 10 to the power of plus 3, it is 4000. 4000 minus 50, it is 3950 ohms. Therefore, B is the right answer because it has to be connected in series to convert a galvanometer into voltmeter. Hence, B is the right answer here. Next problem. What is the value of shunt resistance required to convert a galvanometer of resistance 100 ohm into an ammeter? Here they have given ammeter. You should be careful about the choices. Ammeter of range 1 amp. Given the full scale deflection current of 5 milliamps. Options A 5 by 9.95 ohm, B 9.95 divided by 9 ohm, C 0.5 ohm and D 0.05 ohms. Now here a galvanometer has to be converted into ammeter. How do you convert? By connecting a small shunt resistance in parallel. The value of the shunt resistance Rs is given by Ig into Rg divided by I minus Ig. Now simply substitute the values they have given. Ig is given full scale deflection 5 milliamps, it is 5 into 10 to the power of minus 3 into Rg, resistance of the galvanometer, it is 100 divided by 1 minus 5 into 10 to the power of minus 3. Now here 5 into 10 to the minus 3 and 100. 100 can be written as 10 raised to plus 2, therefore it is 10 raised to minus 1. 0.5 into 10 raised to minus 1 is 5 into 10 raised to minus 1 is 0.5 in the numerator. Now denominator also it is 5 into 10 raised to minus 3, it can be written as 0.1 minus 0.005. Now if you subtract in the denominator, you get 0.5 divided by 0.995. Now, if I shift one decimal in both the numerator and denominator, I will get 5 divided by 9.95 ohms, and hence A is the right answer here. We move on to the next problem. If a velocity has both perpendicular and parallel components while moving through a magnetic field, what is the path followed by a charged particle? It is purely conceptual problem. Now look at the choices. A circular, B elliptical, C linear and D helical. We know that whenever a charged particle is having both the horizontal as well as vertical both perpendicular and parallel components along the field direction, then it obviously describes helical motion. Therefore, D is the right answer. If it has only perpendicular component, it describes the circular path. If it has only parallel component, it will not describe any circular path. It moves in a straight line. You should remember that one. But in this problem, they have given it is having both the parallel and perpendicular component. Therefore, the path is helical. It moves in a helical motion. Next problem. A charged particle experiences magnetic force in the presence of magnetic field. Which of the following statement is correct? Now here the charged particle experiences a magnetic force in the presence of an external magnetic field. Now here they have given four statements. Which of them is correct? A. Particle is moving and magnetic field is perpendicular to the velocity. B. Particle is moving and magnetic field is parallel. If the particle is moving parallel to the magnetic field, it will not experience, and hence B is not the right answer. Particle in the C and D option, they have given particle is at rest. If the particle is at rest, then it will not experience any magnetic force. Therefore, first one A is the right answer. Particle is moving and magnetic field is perpendicular to the velocity. Therefore, A is the right answer here. Next problem. A proton and an alpha particle are projected with the same kinetic energy at right angles to a uniform magnetic field. The ratio of the radii of their paths is. Now this one is similar to that of the previous problem, in which they have given three particles: proton, deuteron and alpha particle. With that knowledge, you can directly answer this one, or simply we will work it out. Options: A 2 is to 1, B 1 is to 2, C 1 is to 1 and D 2 is to 3. We know that kinetic energy is given by the formula K is equal to Q square B square R square divided by 2m. Since the kinetic energies are equal, okay, the radius, it is directly proportional to the square of the mass and inversely proportional to the charge. That formula we know. Now apply the same formula for the proton and the alpha particle. That is Rp is to Ra, that is alpha, is equal to square root of mp, mass of the proton, divided by charge of the proton Qp, is to square root of ma, mass of the alpha particle, divided by charge of the alpha particle. If I take mass of the proton as 1 unit, therefore root 1, and charge is also 1 unit. If I take root 1 divided by 1 is to mass of the alpha particle as 4 unit. Therefore, root 4 divided by charge of the alpha particle is 2 unit, because it is having 2 protons. Now, if I substitute these values, it is root 1 by 1 is to root 4 by 2. Now, root 4 by 2 becomes, it is 2 by 2. Therefore, the answer should be 1 is to 1. Hence, C is the right answer here. Next problem. The resistance of a galvanometer is 2.5 ohm and it requires 50 milliamps for full scale deflection. The value of the shunt resistance required to convert it into an ammeter of range 0 to 5 amps. A simple problem one. The options: 2.5 into 10 raised to minus 2 ohm, B 0.25 into 10 raised to minus 2 ohm, C 0.025 into 10 raised to minus 2 ohm and D 0.005 into 10 raised to minus 2 ohms. We know that a galvanometer can be converted into ammeter by connecting a shunt resistance. Its value is given by Rs is equal to Ig into Rg divided by I minus Ig formula. Now we use this formula, okay. Ig is given, it is 50 milliamps, 50 into 10 raised to minus 3, and R and Rg, resistance of the galvanometer, is given 2.5 divided by 5 minus, that is I minus H. I is 5 amps. We have to convert galvanometer into ammeter of reading 5 times. 5 minus 50 into 10 to minus 3. Now simplifying this one, in the numerator we get 0.125. In the denominator 5 minus 15 to 10 to minus 3 can be written as 0.05. Therefore it is 0.125 divided by, in the denominator it is 4.95. Okay. In the numerator, if I shift the decimal to 2 places, I will get 12.5. In the numerator, I will get 12.5 into 10 to minus 2. Remember that one. Okay. In the denominator, it is 4.95, almost 5. So 12.5 by 5 means it is almost 2.5. So therefore, answer should be 2.5 into 10 to minus 2 ohms. Hence, A is the right answer here. Move on to the next problem. A conducting wire is arranged as shown in the figure. The magnetic field at O is. Now look at the diagram. Here we have a conducting wire having this shape, two straight shapes and two curved shapes as shown in the figure. Now we have to calculate the magnetic field at the point O. Now curved shape, one arc is having radius R1 and the another arc is having radius R2. Now these two arcs are making an angle of 60 degree at the point at which we are going to calculate the magnetic field. That is the net magnetic field you have to work out. Now look at the options. A, mu naught I divided by 6 into 1 by R1 minus 1 by R2. B, mu naught I divided by 12 into 1 by R1 minus 1 by R2. C, mu naught I divided by 6 into 1 by R1 plus 1 by R2. And D, mu naught I divided by 12 into 1 by R1 plus 1 by R2. Now this conducting wire is having 4 segments, 2 straight and 2 arced. Now remember here, 2 straight segments, they are in the same line. That means they are parallel to the line element. Hence they will not contribute for the magnetic field. Only the arcs will contribute for the magnetic field. Now we know the expression for magnetic field due to an arc, circular arc, is given by the formula. We have B is equal to mu naught I divided by 2R into theta by 2 pi. This is the magnetic field. We know that in the case of a circular loop, entire single loop, it is mu naught I divided by 2R. Since we are choosing an arc, therefore we have an additional term theta by 2 pi. Now use this one for the first arc of radius R1. I will write B1 is equal to mu naught I divided by 2R1 into theta is 60 degree. 60 degree in terms of radians is pi by 3 divided by 2 pi. Now pi get cancels, we will get 1 by 6 and in the denominator we have one more term 2. Therefore B1 is equal to mu naught I divided by 12 R1. Clear? Now same is true for the second arc of radius R2. Second arc is also subtending at same angle. Therefore, we can directly write the magnetic field due to the second arc B2 is equal to mu naught I divided by 12 R2. Okay. Now, for the arc of radius R1, the current is clockwise direction. Therefore, magnetic field is into. So, B1 is into the plane of the figure. And current in the second arc, that is of radius R2, it is in the anti-clockwise direction. We know that current is coming out. The magnetic field is coming out. Now here arc of radius R1, the current is flowing in the clockwise, therefore magnetic field is into. For the arc of radius R2, current is anti-clockwise, the magnetic field is coming out. Therefore, what is the net magnetic field? It is B1 minus B2 because these two are in opposite direction. Now, if you work out that one, the net magnetic field is B1 minus B2. Now, B1 is mu naught I divided by 12 R1 minus mu naught I divided by 12 R2. mu naught I divided by 12 is common. If I take it out, it is 1 by R1 minus 1 by R2. Hence, B is the right answer here. Okay. So remember this formula. B is equal to mu naught I divided by 2R into theta by 2 pi for a circular arc. Next problem. A proton is projected with a uniform velocity v along the axis of a current carrying solenoid. Then, options A. Proton move along helical path. B. Proton will be accelerated along the axis. C. Proton will continue to move with velocity v along the axis and proton path will be circular about the axis. Now look here, a proton is projected inside a current carrying solenoid. Now in the case of a solenoid, we have a magnetic field only along its axis and the proton is projected parallel to the magnetic field. Therefore, the velocity of the proton and the magnetic field, they are parallel to each other and hence this proton will not experience any magnetic force. Therefore, magnetic force will not accelerate. And since there is no electric field, there is no acceleration. Therefore, proton move along a helical path. It is wrong because velocity is parallel to the field. Proton will be accelerated. No, it is wrong because there is no electric field. If there is electric field, then only it gets accelerated. But here we are having only magnetic field. Proton path will be circular. It is also D is also wrong because magnetic field and velocity vector are parallel and hence it will not experience any magnetic force. So option C is the right answer. Proton will continue to move with velocity v along the axis. Hence C is the right answer with this formula. F is equal to QVB sin theta. V is parallel to B and hence magnetic force is 0. Therefore, proton simply moves along the axis of the solenoid. Therefore, C is the right answer here. Next problem. A charged particle with a velocity 2 into 10 to 3 meter per second passes undeflected through electric field and magnetic field in mutually perpendicular directions. The magnetic field is 1.5 Tesla. The magnitude of the electric field will be options A 1.5 into 10 to the power of 3 Newton per Coulomb, B 2 into 10 to the power of 3 Newton per Coulomb, C 3 into 10 to the power of 3 Newton per Coulomb and D 1.33 into 10 to the power of 3 Newton per Coulomb. Now carefully look at the problem. A charged particle, its velocity is given, it is passing undeflected. That is velocity selector formula. The velocity selector formula V is equal to E by B. E is the electric field, magnitude of the electric field and B is the magnitude of the magnetic field. Now here magnetic field is given, velocity is given. Asked to find the electric field, therefore electric field is equal to V into B. Now velocity is given 2 into 10 to the power of 3 and magnetic field is 1.5. Simply substitute and simplify. 2 into 1.5, it is 3. 3 into 10 to the power of 3 Newton per Coulomb. Hence C is the right answer here. Next one. In the figure, I1 and I2 are the strength of the currents in the loop and the straight conductors respectively. OA is equal to AB is equal to R. The net magnetic field at the center O is 0. Then the ratio of the currents in the loop and the straight conductor is, now look at the diagram, this is the diagram. Now look at the options, A pi, B 2 pi, C 1 by pi and D is 1 by 2 pi. Now look at the diagram, they have given a circular loop carrying a current I1 having a radius R and there is a straight conductor carrying a current I2 now which is at a distance of, look at the diagram and given data, R plus R, it is 2R. Now they have given the net magnetic field at the center is 0. That is magnetic field due to the circular loop and magnetic field due to the conductor are equal and opposite. If I take BA, magnetic field due to the circular loop are B1, and if I take BB, the magnetic field due to the straight conductor, that is B2, they should be equal. Now, in circular loop, we are having magnetic field is given by the formula, simple formula, mu naught I divided by 2R. In the straight conductor, the magnetic field is given by mu naught I divided by 2 pi R. Okay, those two fields are equal. Now we will use that relation, B1 is equal to B2. Now what is B1? The magnetic field due to a circular loop, that is given by mu naught I divided by 2R, and magnetic field B2 is magnetic field due to a straight conductor, mu naught I divided by 2 pi R. What is R? It is the total distance. Now total distance is R plus R, that is 2R. Should remember that one. So now simplifying this one, mu naught get cancels, 2 get cancels, and R get cancels. Then what is the ratio of the currents? I1 by I2 is equal to 1 by 2 pi. Hence D is the right answer here. Move on to the next problem. An electrical current passes through a long straight wire at a distance of 5 cm from the wire. The magnetic field is B. The field at 20 cm from the wire would be options A 2B, B B by 4, C B by 2, and D B. Now, electric current passes through a long straight wire. At a distance 5 cm, the magnetic field is B. Then, at a distance of 20 cm, what is the magnetic field? We know that in the case of a straight wire, magnetic field is inversely proportional to the distance. With this simple concept, the magnetic field should decrease. It is inversely proportional to the distance. Now the distance is increased 4 times. Obviously, what should be the magnetic field? Magnetic field should decrease by 4 times. That means B by 4 should be the right answer. We can directly answer this one, or we can work out. The magnetic field is given by mu naught I divided by 2R. For the first case, the distance is 5 cm. B proportional to 1 by R. For the first case, it is substituting R is equal to 5 cm, mu naught I divided by 10 pi. Now for the second case, B dash new magnetic field is mu naught I divided by 2 pi R. Now R here it is 20 cm, 20 into 2 is 40. Therefore mu naught I divided by 40 pi. Now therefore B dash by B, if you take the ratio R B dash is equal to B divided by 4. The magnetic field reduces by 4. That is B by 4 is the right answer. B is the right answer here. Next one. A proton and helium nucleus are shot in a magnetic field at right angles to the field with same kinetic energy. Okay. The ratio of their radii. Now look here in this problem, proton is given and a helium nucleus is given. What is helium nucleus? Which is nothing but an alpha particle. Should remember that one. Okay. Now options are A 1 is to 1, B 1 is to 2, C 2 is to 1, D 1 is to 4. We know that kinetic energy is given by Q square B square R square divided by 2m. Since kinetic energies are equal, we know that radius is directly proportional to the square root of the mass and inversely proportional to the charge. Now you should remember this formula, R proportional to root m by q. Now applying for proton and helium. Therefore, Rp is to Rh is equal to square root of mass of the proton divided by charge of the proton is to mass of the helium nucleus divided by the charge of the helium nucleus. Mass of the proton, if I take it as 1 unit and charge is 1 unit. Therefore, 1 root 1 by 1 is 2. What is the mass of the helium nucleus? It is having 2 protons and 2 neutrons. Therefore, there are 4 nucleons. Therefore, root 4 divided by charge is 2 because of the 2 protons. Now substituting that one, root 1 divided by 1 is to root 4 by 2. Root 4 by 2, it is 1. Therefore, we will get 1 is to 1 is the right answer. Hence, A is the right answer here.